All right. We will have to write a book. I say that every year that I should definitely write a book because the stories that happen to me, like, I just can't make that stuff up. People would believe that it really didn't happen, but you truly can't make it up. So, definitely some good ones to tell. All right, so first of all, I want to congratulate all of you for making it through semester one. Not that I had any doubts that you wouldn't, but we survived our first round of finals, so we've only got about 17 more weeks till the second round hits. Woohoo! Semester two is a tad bit shorter than semester one. When I was prepping things out, it looked like it was maybe 17 weeks versus 18 weeks or so. Not that it really matters, but it's just a little bit, oopsie, shorter. And we will wrap up May 25th. So if you're thinking end goals, May 25th is going to be that last day for final exams. So if you backtrack it, it's like May 18th or something is the last day for work. Well, technically it'd be like the 20th or something like that, but that's so far away, I'm probably getting my dates mixed up. So only like 4 more months ish or so left. So we can do it. Um, we will be needing graphing calculators. I do think that the online ones will work okay for this unit. We're going to look at polar and parametric modes. I totally lost my train of thought. Shoot, don't you hate when that happens? It's like polar and parametric modes, and then now it's gone. All right. Yep, totally gone. So I think I was talking about what we were going to do in the unit. We're going to be starting looking at vectors and then switch over to polar and parametric modes a little bit. So we will need that graphing calculator. And I think Desmos has the capability for the polar and parametric modes as well. So we'll rely more on the Desmos graphing calculator if we don't have a handheld one. Do I have any juniors in here? Let's see. Juniors, where are you at? You got lots of juniors in here, right? Woohoo! All right, so just a couple seniors and mainly all juniors in here. So, juniors, the next thing on your to do list coming up is ACTs. Um, so there's two seniors in here. Rachel's also one, so you're not alone, Isaias. So the ACTs are mandatory by the state of Wisconsin. So lucky juniors, everybody has to take that. That is going to be occurring the end of February. So I want to say it's like the 28th and maybe March 1st or the 27th, 28th, something like that. So we will be preparing for that. There's no school technically those days for everybody else, so the juniors can focus on those ACTs. And more information should be coming out shortly regarding that. Now, my juniors in here, did you get any emails yet regarding ACTs? I think maybe you've received one or so. Not yet. I think maybe one might have went out to family emails about dates. Okay, just about the dates, not locations, right? Okay, awesome. So my guess is that within the next couple weeks here, you'll probably be getting more information about your testing location. Um, so just kind of keep a lookout for that, and make sure you keep those 2 days wide open on your schedule so that you can attend those testing sites. My seniors in here, so my two lucky seniors, Rachel and Isaias, you guys have no testing, no state testing this year. So lucky you two. Senior year is the only year of high school, by the way, that has no testing. In case anybody was wondering. All right, with that being said, are there any other major questions regarding semester two stuff? All right, I'll take the silence as a no. then what better way to start everyone's ending a little bit early? Yeah, so everyone's ending a little bit early. It's just easier to have everybody end than just like prepare the seniors differently. It's just easier to do it all as a big group. All right, so what better way to start off semester 2 than with a video clip? Woohoo! All right, so today we are talking about vectors. What is a vector? So how many of you have seen the movie Despicable Me before? So the original, very first one, Despicable Me. Yay! Awesome. So maybe? Okay. In that first movie, the villain's name is Vector, right? So that's exactly the video. Okay, Tommy already beat me to it. But the villain's name is Vector, right? And he describes why gave himself that name. So he's actually using a definition of what a vector is. So believe it or not, they're sneaking math and high level math at that into our kid movie. So take a look at the clip if you haven't already. You might get an ad. I was prompted for an ad. It was like 3 seconds long, so I apologize. It is YouTube. So go figure. Give me a green check once that's played for you. I'm going to have that phrase stuck in my head all day now. Oh, yeah. Vector, because I'm creating crime with both direction and magnitude. All right, what else besides hearing that definition of fighting crime in both direction and magnitude? Because we're not really quite sure what magnitude might be yet. Well, maybe we are from some of our science classes, but we haven't seen it technically in our math courses yet. What else were you able to take away? There's one other little tidbit of information that he throws in there about vectors. It's an arrow, yeah. So when we see our vectors being drawn, they're going to be represented with arrows. So I really love playing that clip because they do go over a lot of information of what a vector actually is. So here you can see that representation with the arrow that he was talking about. We will be talking about the direction and magnitude in just a moment here. And now your vectors are two-dimensional, by the way. They're not working with our 3D space. It is a two-dimensional vector, which is an ordered pair. We do denote it in component form. You will hear that term component form pop up a lot in your homework and the lesson. So component form looks like an ordered pair, except of having your parentheses surround the two numbers, you have the little arrows, right? I don't even know really technically what to call those, but there are these two things on our laptop, right? They almost look like the less than or greater than symbols, but they're the arrows that surround the 2 points A and B. Now, A and B are the components of the vector, okay? This form, the component form, is generally what we call the standard representation. Okay, that's the arrow from the origin out to that point AB. The magnitude that you heard him talk about is denoted with, and I think I'm getting a little bit ahead of myself, but magnitude is denoted with like absolute value signs around that vector. So The magnitude is going to be the length of your arrow. Okay, so if we take a look here, it's actually talking about how long the arrow is. So when we hear that term magnitude, that's what that's referring to. The direction is going to be a degree measure. So how far away from that x-axis is the vector lying, I should say. So the direction is going to be the direction in which the arrow is pointing. It's going to be a degree measure. The 0 at 0, 0 is what we call the 0 vector. That's happening right at the origin, obviously. That has 0 length and no direction. So we still consider the origin, or 0, 0, kind of like that starting location, that middle point of the x and the y axis. Now, because it is an arrow, when we look at notations of a vector, sometimes they give us 2 points, like R and S, so one of them doesn't necessarily start at the origin, and it doesn't have to. So we can put this into component form using a rule on the next slide. I won't get too ahead of myself, but notice the notation that they use. So for this vector RS, they do put an arrow above it. Okay. Now R is talking about the initial point, so R is the starting point, and S is what we call the terminal point. That is your ending point. So the order in which the letters appear in your vector do actually matter, right? So they are important because when we try to put 2 points and create a vector in component form, we have to follow a particular order to do that. So we do need to pay attention at what's the starting point and what's the terminal point. If 2 vectors have the exact same magnitude, which is the exact same length, we call them equivalent. Okay. Any questions with the terminology there? Lots of new things that we're going to be using, but I think that none of them hopefully are too far out there as far as concept-wise goes, and we should be able to reel these in pretty easily as we work with them throughout class today. Equivalent vectors also have to have the same direction. I think so. I don't actually know for that, if they have to have the same direction or not. I want to say yes, but I'm not 100% sure. I'd have to look into that. I know that they have to have the same magnitude for sure. I'm not sure if they have to have the same direction or not. I know, right? Hey, I'm human. I'm not like 100% math genius here. I may have to resort to Google after class to find out. Dun dun dun. Right? All right, so here was that head minus tail rule. We use the HMT rule when we have to put 2 points into component form. So basically, we're taking our 2 points that make up our vector and putting it in the component form with our little vector brackets here instead of our 2 points. So when I said it's important to know the starting and ending point, this is why. When we do the head minus tail rule, we always start with the ending point first and subtract off the starting point. So you need to know which one is your terminal point and which one's your initial point. So it's always terminal minus initial. So in this first one, it says show that the arrow from R to S. So they're actually telling us to start with R and end with S, right? So when I do my HMT rule and to create the vector in the component form, we need to do S minus R and then S minus R. And we're going to do that for the X values of the points and then the Y values of the points. Be careful with the double negatives here though. Remember, two minus signs next to each other does turn into a plus sign. What am I going to get for this component form of vector rs? Oh, look at a heart. I'm guessing that's a 3, right? The bracket with the 3. Gotta love emoticons. Yeah, it is in Valentine's mode, right? That's awesome. All right, now again, the order in which we subtracted there mattered, because if we would have done s minus r, or r minus s, sorry, we would not have gotten the same results there. So we do want to pay attention to what the terminal point is and what the initial point is. Now it says to show it's equivalent to the arrow from P to Q. So P is our initial point and Q is that terminal point. So help me out here as I put these in the component form. What two values should I subtract for the x's here? Yeah, good. 5 minus 2. And then what order should I subtract for the y's? 3 minus negative 1, which turns into a 3 plus 1. So lo and behold, notice we get that same component form, a 3, 4, which means that they are equivalent. All right, any questions with that at all? All right, lots to learn, so we're going to keep going ahead. I think this is one of the more longer lessons. Obviously, the first lessons of the unit generally are, because it's setting us up for what's to follow, right? So there's always a lot of things kind of at the start of each unit. The next thing we're going to talk about is the magnitude. So magnitude, remember, is the length of your arrow. Now, your vectors are denoted by bold lowercase letters. So the two most common letters that they use for vector representations are V and U. Not quite sure why, but generally those are the letters that they like to use to denote vectors. So a lot of the times you'll see V for vector, obviously, right? And then they also like to use U as well. So those are the two most common ones that we'll see. Although they can introduce other letters as well for vectors besides just those. All right, now to find the magnitude, essentially it's like we're using the distance formula because we want to know how long something is. So we are using a version of the distance formula here. You can see that exact distance formula represented with the 2 points right here. I like to always put it into component form first and then just do your a squared plus b squared and take the square root of that. So a lot of the times you'll see me changing our 2 points to component form first to create the vector. And then once I have that vector created, we can find the magnitude using this formula. So this is the one that I would probably lean towards memorizing versus the first version of it. So even though this one is the distance formula, so if you have that distance formula already memorized, there's not really much else you'd have to do. But if it's written in component form for you, you have to know how to relate the distance formula to that to find the magnitude. All right, so let's go ahead and work on finding the magnitude of vector v. Notice that they do give us PQ for that direction, so that helps us with the head minus tail rule and putting this into our component form. So let's start by finding that component form of PQ. What is going to be our component form here? If we want to show the work, we can. Maybe we should start with the x's. We're still kind of brand new to this. So if we start with the x's, what two things are we subtracting? -5 minus a -3. Okay, so that's going to be a -5 plus 3, which is a -2. Here we go. And then what are the y's that we're going to be subtracting? Yeah, 2 minus 4, which is the -2 Tommy had. So I think we just missed the negative sign on one of those, Tommy, which I'm sure you already realized. Okay, now we can find the magnitude because we have just a and b. So to find the magnitude, we're going to square each of them and add them together. And then obviously put that underneath our square root sign. So -2 squared plus -2 squared is our 4 plus 4, which is our 8. Now, if you can simplify your square roots, I recommend that you do that. So let's get a quick flashback here of how we can simplify our square roots. Anybody know how we can break that down? Or what a perfect square is going to be that goes into 8? 4, right? So we're always looking for perfect squares that go into our numbers underneath our radicals there. So we can break that down into the square root of 2 times the square root of 4. We know the square root of 4 is just a 2, but we got that square root of 2 left over. So a quick flashback of our algebra days when we were simplifying those radicals. Okay, so we do want to simplify those when possible. All right, questions with that at all? So the magnitude or the length of this vector is 2 square root 2. Okay, so the next thing we're going to talk about, and this is my favorite thing to do with vectors. I see Zayas' question there. Are decimal answers acceptable? Not really. We do want to leave them as square roots. So if anything, leave it as maybe the square root of 8 instead of turning that into a decimal answer. At the pre-calculus level, we want to try to leave our answers exact as possible when it comes to this stuff. So if anything, I would maybe leave it more as a square root of 8 versus trying to turn that into a decimal. Although we do use decimal answers a little bit later on, but I would generally try to stick to your square roots for magnitudes. Okay, the next thing we're going to talk about are vector operations. So we can add, subtract, and multiply, well, scalar multiply with our vectors. And what a scalar multiplication means is you take an integer value and you distribute that through the vector, essentially. So we're not really going to be multiplying two vectors together. Instead, we're just going to kind of use the distributive property by having an integer value for k. Okay. So those are the three operations that we can do with our vectors. So adding, subtracting, and then scalar multiplication. They do give you some examples of what the adding of the vectors looks like. So kind of two different scenarios. You can add two vectors onto each other. So you start at the origin, and u goes out here, and then v is tacked on to that ending point. Or technically they can be going in kind of two different directions there from the start, and then we can, when we add those together, we still end at that same spot here in the red. All right, let's go ahead and actually practice these operations. So let's start with the adding, and it's just as easy as you would think. When you're adding two vectors, you add the x's together and then you add the y's together. So in part A here, it wants us to take vector u plus vector v. So looking at the x components there to start us off. It'd be a -1 plus 4. And then the y components would be a 3 plus 7. So we're looking at a resulting vector of 3, 10. I know, rocket science, right? We actually really, really like our adding and subtracting with our vectors. All right, what do you think b is going to equal? 3 times vector u. So if you had to make your best educated guess right now, because it's technically our first example here, what do you think the resulting vector would be for 3 times vector u? Yeah, it's exactly that. -3, 9. All you're doing is you're taking 3 and distributing it through the vector u. Good. Now the last one is we have to do a couple of operations here because you have both scalar multiplication and addition. So you're going to have to just kind of do the multiplication first and then your addition second. So you want to kind of follow those order of operations when you have more than one present. So let's start with 2u. So just the 2u. What's the resulting vector of 2u? -2, 6. Great. Now I would like you to go ahead and do -1 times vector v. -4, -7. Awesome. And then lastly, we can add those together. So when I add those together, what is my final answer? -6, -1. All right, the operations with your vectors is, I would say, the least complicated thing that we'll see. So this should be a favorite task for you when these pop up. It's about as basic or as simplistic as we can get when we do refer to our vector work. Any questions? I just want you to take a peek over here as well. So if you have your starting vector u, here's kind of what those scalar multiplicators do. So 2u, you notice it doubles. Half u is only half the length. And then -2, it still stays the same length as 2u, but notice the direction has changed. So that negative makes it go in the opposite direction. Yeah, we got a lot to cover in this first lesson. Okay, so I'm going to go ahead and move forward. The next thing I want to talk about is a unit vector. Unit, what do you hear when you think of the term unit? So what do you think of when you hear that term unit? Yeah, usually it's one of something, right? When you talk about a unit, just a singular unit, it's going to be one of something. And in the past, we always talked about units of measure. So the measure part comes with the feet or centimeters or inches, but the unit is generally one. So when we have a unit vector, we're looking for something with a length of 1. Now, to find a unit vector, if we're given a vector in component form, we're going to use this formula right here. And I would probably just refer to the first copy of it. So you're going to take the vector itself and essentially divide by its magnitude. We can also write that as 1 over the magnitude of the vector and then distribute that through it. Okay, that will help us find the unit vector. So in order to apply either one of these though, we have to find the magnitude. So let's look at our example below. It says find a unit vector in the direction of -3, 2 and verify that it has a length of 1. So we're going to have to start by finding the magnitude of that vector. So what's the magnitude going to be? Notice it's already in component form. So if it's already in component form, yeah, you're going to square each of those and add it together. So -3 squared is 9. 2 squared is 4. So that's going to give you the square root of 13. Now we cannot break down the square root of 13. There are no perfect squares that go into that. 13 is a prime number. So to find the unit vector, we're going to take 1 over that magnitude, so 1 over the square root of 13, and we're going to multiply that through the vector v. Oopsie. Okay, so essentially what that would finish off as is a -3 over the square root of 13 and a 2 over the square root of 13. And technically, we don't really like to leave those square root of 13s there. So if you wanted to rationalize the denominators, you could. But for now, we'll just go ahead and actually leave that with the square roots there. Now, to verify that it has a length of 1, what you would do is you would take the magnitude of this vector. So real quickly here, I'm just going to do that because we're running out of time and there's still a bunch of stuff we have to cover. To find the magnitude, you square each piece. So that would be a 9 over 13 plus a 4 over 13. And we notice that when we add those fractions together, we get 13 over 13, which is just a 1. And the square root of 1 is 1. So we did find that unit vector correctly because it does have a magnitude of 1. Okay, questions with that at all? Okay, the next thing that we're going to talk about real quickly here is something called resolving the vector. Before I get there though, I do want to talk about the linear combination. We saw linear combinations a little bit in Algebra 2. Remember when they used I and J behind things? And maybe we don't necessarily remember that because it's been a while. But basically, if you see I and J, I is just referring to the first component of the vector, and J is referring to that second component of the vector. So if you needed to, you could go ahead and just take the number, the first number here, and put an I behind it, and the second number here and put a J behind it. So just note that it works both ways. If you have this linear combination, you can just backtrack it to the vector here by pulling the coefficients in front of each letter. So nothing too spectacular with that linear combination. Definitely don't overthink it. It's just pulling the coefficients to get it back into that component form. Okay, I do want to talk about resolving the vector because that's going to help us find the magnitude in specific examples. So we do want to go ahead and copy this down. A vector v can be written as the magnitude of v times cosine of theta and the magnitude of v times the sine of theta. So if we look over here, we can relate our trig using sine and cosine back to that vector. Again, resolving the vector will help us find the direction. I think I said magnitude, but I actually meant it'll help us find the direction of a vector. All right, let's go ahead. And again, I just stole that right from the textbook, so if I'm going too fast at this point, I apologize. I just want to make sure we get through some of these core examples so that you can attempt the homework assignment. All right, it says finding the components of a vector here. Find the components of vector v with direction angle 115 degrees and magnitude of 6. So basically that is writing your component form of your vector. So in order to do that, we're going to go ahead and use that resolving the vector. So we had, if I look back here, your component, your vector itself, will equal the magnitude times cosine of your direction, and then your magnitude times sine of your direction. So to find this component form, we take the magnitude of 6, and just like your unit circle, that first term is going to be your cosine representation. And then the second term should be your sine. Remember, in the unit circle, cosine represented your x and sine represented your y. That's still applying here with your vectors as well. This time you will, it says using no technology, so technically this would be the answer without using technology. We can go ahead and put that in decimal form, but with using our calculator though. So make sure you're in degree mode, because 115 degrees, and let's actually find the quick decimal representations of this component form. So what is 6 times cosine of 115 degrees? A negative 2.536. And Rebecca seconded that. Awesome. And then what is 6 times sine of 115? Approximately 5.438. Good. So if they ever do ask you for the decimal representation, just grab that calculator and punch it in real fast. If they say to use no technology, this would have to be the answer you leave it as, the one that's boxed. So technically, this point out here, the V for A comma B, is this location right here, these numbers. Questions with example 5 there and creating the component form? All right, next we're actually going to work on finding the direction then. So it says find the magnitude and the direction angle of each vector. Now, resolving the vector requires us to use the magnitude, so we do want to start off by finding that first. So let's start in part A here. What is the magnitude of u? So the magnitude of u is going to be the square root of 13 again. Okay, popular one, right? Because 3 squared plus 2 squared is 9 plus 4, which gives you your 13. Now, if I think back to my resolving vector formula, I have my vector equaling, and I'm only going to do the x version of it right here. Technically, you can use the y version, but I'm just going to stick with my cosine value. So because I'm looking at the x right here, I'm going to look at the x term of my vector. So I am looking at 3 because that's the x term of the vector. I'm going to let that equal this first part of resolving the vector formula. So that means I have to take the magnitude of the entire vector, which we said was the square root of 13, and multiply that by the cosine of the direction, which is what we're trying to find. So before we go any further, are there any questions with how we set that up? So using the resolving the vector formula, I took the x component of that formula and set it equal to the x component of the vector we had. Yeah, you could essentially set the y's equal to each other and come up with the same answer. So if you prefer to look at the y values of things, that's fine. You should come away with the same answer in the end. So now it turns into how do I solve for theta? So anybody remember our steps on how we can solve for theta? Divide by the square root of 13. All right, one last step, arc cosine. Yep, use cosine inverse and make sure you're in degree mode and typing this in appropriately in the calculator. If you're not putting parentheses around things, it's going to yell at you. So about how many degrees is theta going to be? A 39.23. Can anybody second that result? Okay, got a little bit differing, a 33.69. Let's go ahead. Anybody second that result? Here's how I type it in. Oh, looks like I got, oh, there you go. Thanks. 33.69 is what we'll go with. All right, before we box up our answer though, we have to make sure that that direction makes sense for the vector we're looking at. So 3, 2, if we think about 3, 2 in terms of a point, that falls into quadrant 1, right? So quadrant 1 is over here with that 3, 2. Does 33.69 make sense for the direction angle there if that vector falls in quadrant 1? Yeah, right? 33.69 is in quadrant 1. So sometimes there might be additional steps we have to take to get the appropriate angle measurement with regards to where that vector is falling. But since it makes sense, it fell into quadrant 1, we can box that up. In the second example here, we're not going to be quite as lucky. So let's go ahead and take a look at that. Let's start with the magnitude of V. What is going to be the magnitude of V? See, 4 plus 25 is the square root of 29. Good, I agree. So using that same general idea, we're going to pull the x component of the vector and set that equal to the x component of resolving the vector. So that's the magnitude times cosine of our direction. We can divide and then use the arc cosine. So saving us a little bit of time here. Let's go ahead and punch this into the calculator. What do we get as the result then? We should get 111.8. Yeah, we should get around there. Let me just double check. -2 divided by the square root of 29. Oopsie, there we go. So 111.801 or 0.8. All right, does that make sense for the vector that we're looking at? So when we, okay, good. When we plot this vector, it's down in quadrant 3. Is 111.8 in quadrant 3? No, it's not, right? It's actually out in quadrant 2 somewhere, like right around here. So how do we get to this spot right down here instead? So essentially it looks like we want to reflect it over the x-axis almost. So to do that, we've got to actually subtract and go this way around from here, right? Kind of take the negative approach to it to find that degree measure of the other way. So let's go ahead and take the 360 degrees because that's the full time around and subtract off the 111.8. Because if I do that, I start, basically that's telling me I start right here, but subtracting that off is going this way around. And that should put me out in quadrant 3 somewhere. So let's go ahead, and what is going to be that degree measure then? A 248.2. Now 248.2 is much better direction because that does fall into quadrant 3. So essentially what that's saying is that direction is 248.2 degrees from this starting axis over here. So it's 111.8 going the opposite direction, this negative route, but 248.2 going the other way. Does that make sense to everybody? So sometimes when we get that direction, we've got to make sure it matches up to the correct quadrant. If it doesn't, we have to subtract from 360 to get there. So a tad bit confusing with that, but we always just want to make sure we're checking quadrants to make sure the degree measure matches. I think it has to do with the negative numbers. I'm not quite 100% sure with that, but I think it has to do with the negatives that are in that component form somehow. Yeah, I'm not 100% sure, but that's the first thing that kind of sticks out to me on why that extra piece has to be added in there. Okay, we kind of ran out of time, but the good news is we kind of hit everything we needed to. We'll just do this one real fast because it's really not that big of a deal to complete this one. This is example 7. It's the last example in the textbook, I believe, that you need to get through before you can try the exercises. So it says the velocity of a moving object is a vector because velocity has both magnitude and direction. The magnitude of velocity is what we call the speed. So a DC-10 jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. So that 500 miles per hour is the speed it's going. That's what we can denote as our magnitude, right? So I'm going to go ahead down here and just say the magnitude of this vector is 500. Because we're looking at a bearing of 65 degrees, note they have right here that the bearing is the angle that the line of travel makes with due north. So if this were to be a compass, never eat soggy worms. North is this top of the y-axis here, right? So due north is this top of the y-axis. So technically, in a clockwise direction, 65 degrees is this measure here. So the angle that we want to use in our component form is the 25 degrees, because together those make up a 90-degree angle. So doing 90 minus 65 gives you the direction angle that we want to use of 25 degrees. All right, because we have that, we can go ahead and find the component form. The component form, remember, we can use our resolving the vector formula. So we can take magnitude times cosine of direction, and then magnitude times sine of direction. So using a calculator here, what are going to be the approximate decimal answers of this vector? So 453.15 to 11.31. Anybody second that? Awesome. Perfect. So it's not like this one was anything too challenging. It's just knowing what each of the terms actually meant there. So knowing that speed is your magnitude, and then knowing the the bearing location to help you find the direction of the vector. Okay, and then obviously using the vector formula there. Okay. We didn't have time for 2 of the practice questions, but they're nothing major. I'm confident that you guys can kind of figure those out on your own. So go ahead, give 6.01 lesson a try. If you have any questions, bring them to Wednesday's class. We'll start off with that. Otherwise, not Wednesday's class, Thursday's class, sorry. Otherwise, I will see you guys again Thursday morning where we'll take a look at 6.02 lesson. All right, bye everyone. Have a great day.